I'm happy to hear your cries for mercy. A couple of things to note, though, since I've got this up here, uh, is when I added up the total number of points that were available, turned out there was 102. And so I thought, the first two questions or the first 2 points that you lost don't count. So in other words, I took 102, subtracted whatever you got next. So if you do the math, it doesn't work out. So anyway, it's out of 100 on Moodle, but it's out of 102 when I did the calculation. Just so you know. A couple of things that a lot of people got wrong. I just want to hit really quick, and then we'll move on to the new stuff. Numbers 4 through 9. Just a couple of things. Some of you, actually a couple of you, maybe 3 of you, decided you didn't like this sine of xy, and so you just ignored it and just did this. and actually at least one of you, I can't remember how many, but at least one of you did the opposite. You're like so focused on the sine of xy that you ignored the polynomial part. But let's do this really quick. Maybe I should have put a little bit more space there. I don't know. But I'm not going to do the whole thing, but I just want to point out a couple of things because this was a common thing to get wrong. So sine of xy, the derivative of sine is cosine. Don't forget the chain rule, though. The derivative of what's in there is y with respect to x. So you're doing the derivative of xy with respect to x. It's hard, and it's a one that like half of you got wrong. So if you got it wrong, don't feel bad. Then, of course, this is 2x, and then this one is just 2y to the fourth because you're just dealing with x. So y is a constant with respect to x. If you get that one right, you probably got all the rest of them right, except for possibly over here with the directional derivative. But I tried to I made a nice unit vector. Thought it would be easy for you, but it wasn't as easy as I thought. Okay, so that's that. If you do have it, well, here, let's go on to the next one I wanted to talk about, and that's this one, because I don't know what went wrong here, but there's such a variety pack of answers. So let me remind you, velocity is the derivative of position. Maybe if I had harder problems, you would have been okay. But 2tj plus 1 over tk. So there's the velocity, and we want the velocity at 1, which is 2I plus 2j plus k. And some of you, actually a considerable number of you, dropped the I, j, and k and just got 5. But velocity is a vector. It's a vector. It's pointing somewhere. So leave that in there. Acceleration, the derivative of velocity is acceleration. So you have let's see, that's just going to be 0I, because I'm doing the derivative of this up here, plus 2j minus 1 over t squared k. If that bothers you, write it as t to the negative first power, and then you'll get this right. But anyway, now that I've got acceleration, I want a of 1, which is 2j minus k. Because 1 over 1 squared is 1. So I know this is a little babyish to go over this, but this one, there were so many problems, I wanted to make sure we hit it. And then the unit tangent vector is just the unit, or not the unit, the velocity over the speed. So there it is. So I just take this thing, so it's going to be 2I plus 2j plus k, and divide it by this thing, 3. Oh, haven't done that one yet. That's okay. It's 3. We'll get there in a minute. So yeah, you can write it as 2/3, 2/3, 1/3, or whatever. But yeah, so you get a vector. It's still a vector. It's a unit tangent vector. These are all vectors. Okay, next one. Speed is the first one that's not a vector. It's the magnitude of the velocity. And so we're going to do the square root of 2 squared plus 2 squared plus 1 squared, which is the square root of 9. I was careful about my numbers so this would come out nicely. I thought it would be easy, but apparently it wasn't. Okay, this isn't easy though. So, and here I have to, I realized there's multiple ways of doing this. So if I had to go back and regrade a few of yours to, because I was like, wait a minute, that you did something okay, maybe something approaching something good. But here, what we're going to do is we're going to do the derivative of the speed. That's the easiest way to get the tangential component of acceleration. So I need to do the speed in terms of t. So that's going to be the square root of 2 squared plus 2t squared plus 1 over t squared. So let's see, this is going to be the derivative of that thing up there. It's going to be 4 plus 4t squared plus 1 over t squared. So you could just, and several of you actually just did the derivative of this. But it turns out that that is a perfect square. And so you actually end up doing 2t plus 1 over t, I think. Is that what it ends up being? Let me see. I'm trying to do it in my head. 2t squared. Wait, did I blow something here? 2t squared plus 1. That's it. Okay, yeah, that's what it was. Okay, yeah, so that's, yeah, you can rearrange this, I guess, so if you want to do the algebra, we can do it later. We don't have to do it now. Come see me in my office. I'll show you how the algebra works. But there's some algebra that will turn this into just this nice fraction. And actually, even that's not simple enough for me. I'm going to write it like this, as 2t, whoops, not equals. It's not equal yet. I'm doing the derivative of 2t plus t to the negative first. So you can separate this into two fractions, 2t and t to the negative first. Yeah, and so then this is just 2 minus t to the negative second. And then when you plug t equals 1 into this, you get 1. So plug 1. So a sub t at 1 is 2 minus 1, which is 1. Now, this is a little confusing. Some of you did the wrong thing, completely wrong thing, and got 1. So if you did completely the wrong thing, I didn't give you any points. Like, for example, if you do this, if you do a of 1 and you leave out the j and the k, you might get this, which is also 1. So I'm going to see some supporting work. In other words, if you just have 1, or if you've done the wrong thing. Now, there were a couple of other ways you could do this. There's the derivative of the tangent vector divided by the derivative of the tangent vector divided by the speed. I think that's one way. I forget. I think that may be one of them. But there's a couple other ways to get this that are harder, in my opinion. A couple of you were successful with that derivative of the tangent vector thing. I think I gave you credit for that. But that was hard. So that one was hard. Here I gave you the wrong, so the kappa, I gave you the wrong, only one of you asked. So I was kind of sad about that. But I meant I should have a 3 there. It should be cubed. But I accepted, what was it? You got 2? I think you got 2 if you did it without the cube. When I did the key, I didn't even look at the formula because I'm like, oh, I know how to do this. But here again, there's some other ways to get this. That's not the only formula for kappa, and I tried my best to identify if you did it right. But if you think that, if you think I got it, if you think that I've done you dirty, I can always. So here's the correct answer: 6 over 27, which is the same as 2/9. The incorrect answer that I also accepted because I have the wrong formula there is that. So either one of those. So if you have one of those, I probably marked it right, even if you didn't use my formula. You have at least that one. So anyway, there's that. I don't think there's anything else to talk about that I care about, but you might have stuff you care about. If you do, stick around afterwards, and I'm happy to chat. But we do need to move on because we have several things. This is going to be a little bit of work to do today. First things first, we have some homework. Homework? Did you not look at the homework? You were supposed to what? Go on a hike, play board games, and then there's a bunch of stuff. Maybe that's over Thanksgiving. Make sure you check the homework for Thanksgiving as well, because there's stuff that you should be doing. It doesn't involve calculus, but for calculus there was homework. If you didn't notice it, you can always do it for tomorrow, I suppose. But it was these problems here. I forget the exact numbers, but if we need to, we could do one of them. I don't want to do them all. But is there one that we need to do that was, yeah, you got one, Ryan? 16, was that the best of the bunch? Let me see. Oh, yeah, that one is a good one, isn't it? Yeah, let's see. If we can do 16, then we can do all of them, right? Okay. So let's do 16 really quick here. Come on, have no fear. Okay, let's just done. Copy and delete. Okay, let me go find some space to do this. Just a sec. There it is. Okay, so we're supposed to find critical points and classify them. That's basically it, right? So let's do our derivatives. I know you're scared of your derivatives, but this isn't that bad. Put this over here. Okay, so here we go. F sub x, I'm going to use the product rule. Okay, so let me just say what I'm going to do ahead of time, and then I'm going to just do it. Product rule and chain rule. When I get to that e to the whatever, that's the chain rule. And the y, so f sub x, the y is irrelevant. So let's see. You have y e to the negative x squared plus y squared over 2 minus 2x squared, I guess just a minute, over 2. 2x squared over 2. I'm going to make sure I get this right. Y e to the negative x squared plus y squared over 2. Okay, so I believe I got that right. So just to show you, you have the product rule. You can see there's the two things. This is the derivative of xy with respect to x. And here, well, embedded in here somewhere is the derivative of e to the negative. So e to whatever, you just write the e to that. And then do the chain rule. So the negative 2x, there's the 2 down there. And then you've got a second x that just came along for the ride from the product rule. Okay, so there's my f sub x. F sub y is going to look suspiciously similar. I'll put it over here. X e to the negative x squared plus y squared over 2 minus 2 y squared over 2 x e to the negative x squared plus y squared over 2. Okay. Let's factor these. We're going to set them equal to 0 and factor. I'm going to do two things at once. So we have y e to the negative x squared plus y squared over 2 times 1 minus x squared is equal to 0. And then this one, set this one equal to 0. It's going to look almost the same. E to the negative x squared plus y squared over 2 1 minus y squared. So just so you know where everything came from and where it went, the y, of course, comes from the fact that there's a y in both of these, that exponential in both of them. And then there's one of these, x squared of these. Same thing goes here. Now let's go ahead. We'll take this separately one at a time. So we have, on the left, you have y equals 0, or e to the negative x squared plus y squared over 2 equals 0, or 1 minus x squared equals 0. It's a product. You have three things. One of those has to equal 0. But the middle one can never equal 0, so I don't have to worry about that. So this, I'll just put an x there. It doesn't. This one is already y equals 0. This one, I hope you recognize, x is plus or minus 1. So far, so good? Yes. Now you have a couple of choices. Choice number 1, take each of these three, that and these, plug them individually into this. So for example, I would plug y equals 0 into this, solve for x. Plug x equals 1 in this, solve for y. Plug x equals negative 1 into this, solve for y. Fortunately, though, this is such a simple equation that I don't need to do that. It gets the same factors, x equals 0, or 1 minus y squared equals 0. So x equals 0, or y equals plus or minus 1. The long and the short of it is that if you let y equal 0, then x equals 0 is your only option over here. So one of the critical points is going to be 0, 0. And then if you let x equal positive 1, both of these are possibilities. And if you let x equals negative 1, both of these are possibilities. So there's actually 4 critical points. So 1, 1, 1, negative 1, negative 1, 1, negative 1, negative 1. We're almost done. I know you punish me with my own problem that's the hardest of the bunch, but it turns out it's not so hard, is it? So I need the second derivative in the x direction. I need the second derivative in the y direction. I need the mixed second derivative, and then I'm going to get a d here. So we're going to do this almost done. So the next step is to compute second derivatives. Yes, pain. It's going to be okay. I think I'm going to use the factored version to get my second derivatives. So give me a sec here. Copy this down to here. I'm just going to put it down here. Okay, so this is f sub x factored. And then I'm going to get f sub xx using the product rule again. So, but I'm going to use this factored version. That way I only have to use the product rule once instead of twice. So we have, let's see, the derivative of the first thing, that's the painful part, is going to be negative xy e to the negative x squared plus y squared over 2 times 1 minus x squared minus 2xy e to the negative x squared plus y squared over 2. There, I think that's it. So here, I know you're confused about where everything went. So here is this thing and its derivative, and then the other thing is that thing and its derivative. I think I got that correct. Okay, now I just have to use that. In fact, let's make it simpler yet. So this is going to, looks like I can combine these, can't I? No, I can't. Yes, I can. I have negative xy e to the negative x squared plus y squared over 2 times x squared minus x squared minus 1. No, wait, there's a negative, double negative, and x squared, that'll be negative minus 3. Does that look right? Let me just check. So the x squared is obviously from here, and then double negative, and then the 1 is going to be negative 1, and this is negative 2. So negative 3. I think that's it. Okay, so f sub yy, because of symmetry, is going to be the same basic structure, except for this. You can go through the trouble of doing it if you want, but that's what it's going to be. Trust me on this. And then I need f sub xy, which I'm going to go back to this, use the product rule again, and I get e to the negative x squared plus y squared over 2. Sorry, these should be in parentheses all the way down the bunch. Okay, times 1 minus x squared, and then minus the derivative of that. Give me a sec here. That's going to be y squared e to the negative x squared plus y squared over 2 times 1 minus x squared. Oh, interesting. Okay, so f sub xy is 1 minus y squared, 1 minus x squared times e to the negative x squared plus y squared over 2. Okay, I'm getting really sketchy, aren't I? But here's the deal, is that e to the negative x squared plus y squared over 2 is always positive. So when I go up top, I'm just going to, this thing here, always positive. This thing here, always positive. And this thing here, always positive. So since all I really care about is whether these things are positive or negative, I do need to know how big they are. Oh, but they're the same. It's the same. I'll just factor them all out. Yeah, it's the same. All three of them have that factor. So all I'm going to compute is this other stuff. So we've got negative xy x squared minus 3, and this is negative xy, y squared minus 3, and this is going to be whatever's left over, yeah, 1 minus x squared, 1 minus y squared. All right, I love it. And then we'll do d. Okay, so this is going to be 0. This will be 0. This will be 1. This will be negative 1. Okay, how did I get d? Remember, d is this thing times this thing minus this thing squared. So that is a saddle. Saddle. Okay, next one. Let's see if I can do this quickly in my head. Negative, negative. We have negative 1 times positive, positive 2. Positive 2. This is also positive 2. This is 0. So that's going to be 4. So that's going to be a min. How I know it's a min is this is positive and both of those are positive. When these are both positive, then you have concave up, minimum. Okay, let's see. Give me a sec here. This will be, sorry, negative 4, negative, 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 negative. There's triple negative there. That's 2. This is 2. Wow, this is also a min? Am I getting that right? Hold on, let me do the next one really quick, carefully. So plugging in 1 and negative 1 into these things. So 1, negative 1, I get 1 times negative 1. That makes this positive. 1 squared minus 3 is negative. Negative 2 times positive 1. That'll be negative 2. This will be also negative 2. Oh, fascinating. This is really interesting. So this is a max. And this is also negative 2. Wow. So you have these. How could this be? I don't even know what this is going to look like. You got 2 maxes and 2 mins surrounding a saddle point in the middle? That's incredible. I'll have to do this on the computer to see what it looks like. Maybe I'll have to actually 3D print it because that seems like this would be exciting to have a model of, if this in fact is what it is. Okay, so if I've done my math right, but the general idea, hopefully, I may have made a mistake algebraically because I'm doing it quickly and I know that we need other stuff to do. So if you see something that I've made a mistake on, I'll figure it out by next time because I'm going to actually do this on the computer because this seems like an interesting 3D model that I could have. Maybe I'll add it to my collection. Okay, let's move on though to new stuff. So we've done test, we've done at least one of these. The rest of them are the same idea. We're going to be doing some practice with this. So here we go. First of all, though, I have an easy problem for you. Someone walked in and said, is that what we're doing today? Yay. Okay, so here's the deal. I want you to find the absolute max and min for this function. Min, okay, I can't write. For this function on this interval. Find the very biggest and the very smallest that it can be. I'm going to type it into my calculator because I want to see what this looks like. You can work with a friend if you need to, but this is Calc 1, Calc 1. So joy and happiness, Calc 1. By the way, if you're not as quick as me at graphing, I've got the graph of this function here from -2 to +2. So you can actually see what the function is, and that might clue you in as to how you're supposed to find absolute maxima and minima. So anyway, there's the graph. How high does this get? How low does it go? Those are the sorts of questions that we're interested in. Let's find a random person. All right, let's see how we're doing. I know you're not done with this, but we got to get started and be in the same page, so to speak. Madison, what's the first thing you're going to do to solve this problem? Absolutely. It's the first thing you do with everything in Calc 1, isn't it? Take the derivative. All right, let's see. Daniel, you got the derivative of this thing?
12x cubed minus 24x squared plus 12x.
Wow, it looks like someone did made this problem easy for everybody, hopefully. Let's find out. You're not here, but I know you know how to do it. Emily, what do you do with this derivative now that we got it?
You set it equal to 0.
This sounds familiar, doesn't it? So set it equal to 0. I'm sure you all can factor this, especially since I made this easy for you. So it's x minus 1 times x times 12. Does that look right for the factors? That's some nice factors. And so we've got x equals 0 and x equals 1 are the only solutions. So which one of those is the minimum and which is the maximum? That's what we have to do, right? So let's find out. So next, Tyler, what's next on our agenda? Ooh, second derivative. There's where I'm going to diverge from you. So if we're looking for relative maxes and mins, we would do second derivatives. So that's a good review, though, of what we did for class today, is finding like classifying these things, which of these is a maximum, which is a minimum on this. But now we're doing something a little bit different. And what we're doing is we're saying of all the maxima, of all the points that you see here that are like hills, which one is the tallest? That's not a good example. Here, this is a better example. Here we go. So here, this one, we have a couple of hills here. So you see there's two that go up here. Where is the max, the very tallest, and which one is the very lowest point? That's what we're looking for, absolute max and min. So this would help us though, but I don't want to do it, too much work. So there's another thing that we're going to do, though, that you might remember. It's been a while, probably, since you did this back in Calc 1. And maybe instead of picking randos again, I'll just say, does anyone know what you do? What's next? Yeah, what do you think? No, I don't even want to do that. So I want to know, here, let's look at the picture here real quick. without doing any calculus, if you saw this picture and I asked you, where is the highest point? What would you say? Over here at x equals -2. That's the highest point. And where's the lowest point? It's kind of hard to tell because the graph is, but it's right there, isn't it? So basically at this point, now that we have the 0 and the 1, the 0 is this right here. It's that flat part. The 1 is this flat part right here. Now that you've got those, all we have to do now is just say, okay, the absolute tallest could either be one of those 2 points or it could be at the end points. Is it ringing a bell now? And then the same thing for the minimum. The minimum is either going to be one of those 2 or one of the 2 endpoints. So let's actually check. And the way you check is you may have, this comes in different names, but I've heard it be referred to as the candidate's test. So you have a candidate, and then you have the function value. Whoops, let me fix that. That look better. So the candidate is going to be something like x, and the function value will be f of x. So the candidates are these, the critical points and the endpoints. Where did I get 2 and -2 from? Well, I could get it right from my graph, or better yet, I can get it right from there. That's where the endpoints come from. So back in Calc 1, hopefully you learned something like this, where to do the candidates test, you take all of the critical points in your region. So of course, if one of these was like 7, if it was x equals 7, you would not use that. So all the critical points in your interval, sorry, I'm thinking in terms of 3 dimensions already, all the critical points in the interval and the endpoints. So the endpoints, and then we just compute the function. So let's go up here, compute the function value at all of those points. So I need to copy this so I can do it. Copy, paste. You know what? I don't want to do that. I'm too lazy. So here's what I'll do. Here's my function. It's so big. Here's what I'll do. Since I've already typed it into my my calculator, I'm going to just go to the, where is this thing? The table. Okay. We got to go all the way up on the table. Come on, there's got to be a quicker way. What if I just type 1? Nope. Okay, it's going to take a minute because it's way down at 200. I'm scrolling upward. I'll get to it soon. There's got to be a better way. Just a sec. Table setup. Yeah, that's it. Table start. That's it. I found it. This is so much better. Okay, let me show you what I have on my table. So this is basically the function values that, let's see, camera this thing. Here we go. Zoom in so you can all see and enjoy. So if you have a fancy calculator like mine, you can actually use the table feature once you've typed in the function. You don't have to do this. I'm just, like I said, I don't want to have to compute that function at each of these points. So that's why I'm using the table feature here. But you can see that at 0, here, let's see, I don't even need all of that. Let me crop this down a bit. Crop it down. This is all I really need right here. There. Okay, so that portion is all I really need. So x equals 0. The function value is 12. X equals 1, the function value is 13. X equals -2, the function value is 148. And then x equals 2, the function value is that 20? 20. Okay, now, I always like to tell my Calc 1 students that at this point, you go find your little brother or sister, give them this list, and ask them which is the biggest number on the list. That's all you have to do. Find the biggest number. And so the max is 148 at x equals -2. The minimum is, The minimum value is 12 at x equals 0. That is the answer for the absolute max and min. You will have one max, one min. Now, it might be that the maximum is at two separate points. Like with this one, you can kind of see that these points, this is symmetric, so you have some points that you're going to share the same height. But there's going to be, yeah, it's a max min, one value. So you might say it's 148 at these 2 points, if there were more than 1 point. Okay, so that's Calc 1. We have 25 minutes to do Calc 3 version. Okay, let's do the multivariable version. So here's the multivariable version. You'll notice the difference here is I've got now this thing. This is that function. So this peach-colored thing is that function. And not only that, I've chopped it off. You can actually see visually where the maxima are. In fact, what I could do, oh yeah, just a minute. Can I do this? I can. Just a sec. I gotta take a picture of this. Just a minute. Let's see, can I get a good shot? I don't want people in my picture. Okay, I'll crop you out. Don't worry. I'll crop you out. That way no one has to be embarrassed. Let's freeze. Just a sec. Okay, crop. Just a sec. Crop. Oh, I can get, okay, there. Good enough. Sort of, whatever. It's not as good as I thought, but okay. So I guess what I want to show you here is that you can see that I turned it upside down. That where this thing is touching, and I know there's a little bit of, it's kind of got a little furry or whatever, because it was really thin, the material. But the hump here, right here, is not as high off the ground, because I've got it upside down right here. This hump is not as high as this part right here. So the maximum for this surface is actually these 4 humps up here. So there's actually 4 places where you have a maximum. We're going to have to figure out where those are. So it's a bit of a pain. And then the minimum is probably over here somewhere. Yeah, ooh. Why did I choose that? Okay, the other one we're going to do is this one. This one's a little bit easier. You can actually sort of see here that you have a maximum, this hump here. But these 2 peaks here, they look like they're almost the same height as that. We're going to find out which one is the highest. And same thing with the minimum. The minimum you can see isn't there. It's the darker. And then there's also these like edges that go down lower on the edges. Okay, so here's the deal, is when you're dealing with multivariable functions, you're interested in the max and min over a region. So this is a region. So to do this, we're going to do the same things that we did up here, but we're going to do it in multivariable land. So the first thing to do, and this is super important, even though it feels kind of silly, but the first thing to do is to sketch the region. So sketch the region, sketch. That's step 1, sketch, nope, if I can spell it, sketch. Okay, we're sketching the region. So this goes out to 3 halves, back to -3 halves. Here's 1. There we go. Here's 1. Here's 3 halves. Here's 1. Here's -3 halves. Okay, so this region, it's kind of like a top-down view of this model that I have. Okay, there, good enough. Okay, that's really a poor representation, but it's the way it is. So if you think of taking this thing and looking at it from the top down or the bottom up, it's a big square. That's all it is. So that's what this is. It's a square. So we've got this square region. So that's step 1, sketch the region. Step 2 is find the critical points. Oh no, well we did this before though. So we did do this. We did this last week sometime. So I'll just tell you what those critical points are. You could probably figure it out by looking at this. So the critical points in the region. So these are, maybe I should call them region critical points. So the region critical points, I will make a list. It will start right here. Give me a minute here. This is going to be X, Y. These are the critical points. And this is going to be f of x, y. I'll put that over here. So give me a sec. 0, 0, 0, 1, 0, negative 1. 1, 0, 1, 1, 1, negative 1. Give me a minute. Negative 1, 0, negative 1, 1, negative 1, negative 1. Wow, so many. I'm beginning to regret my choice. Okay, so each of these is a potential max or min. Now you'll notice on my model, if you can see my model, you can actually see those. We computed those last time, last week sometime. You can see them on here. They are the relative maxes, the relative mins, and these saddle points. There are 5 saddle points. Obviously, the saddle points are not going to be an absolute max or min, but I wouldn't necessarily know that because I wouldn't necessarily have printed this out and had the model to touch. So those are those 9 points, critical points. That's why there's so many of them. So there they are. So we find the region critical points. Number 3. Number 3. Let's see, we need to do the same thing, something that is analogous to what we did up here. Up here, you did critical points and end points. Remember, it was the end points and the critical points. So if you had to describe to me what is equivalent to an end point on this, what would you describe? What's an end point on this thing? A corner, yeah. A corner is like an endpoint, isn't it? So each of these corners, and those aren't good examples of this, but this is a great example. You see this function? Maybe I should have picked this. This is an easier function. But here, you can see that these corner points, they stick up way above the rest of the function. You can actually see that. And so this one, the corner points, are the critical points. Or are not the critical points, they're the maximum right there. And in fact, this corner point here, these two, they look like they're going to be the minimum down there. So let's get the corner points and put them on the list. So number 3 is going to be corners. Corners, and that's easy. 1, 2, 3, 4. This is why I have you sketch the region, is so that you can see what it looks like. Make sure that your critical points are inside the region. So let's see. Okay, it's going to be all right. This is going to be 3 halves, 3 halves. Negative 3 halves, 3 halves. Negative 3 halves, negative 3 halves, and 3 halves, negative 3 halves. They're the 4 corner points. Ugh, that's so nasty. Okay, so these are the corners. These are the critical points. Region criticals points. But there's one more type of point that we have to account for, unfortunately. So that's, once you get a third dimension, we have the critical points, just like in Calc 1. Corner points, just like Calc 1, if you think of the corner points similar to the way you think of the endpoints. Let me see if I can find an example of something where, yes, here we go. This is a good example. No, that's no good. Just a minute. That one. This is a good one. Okay, yeah. This one's good. Okay, so with this one, you can see that the corner points are all kind of in the middle. They're like they're not all that high, they're not all that low. But do you see where the minimum is for this? I mean, the maximum is clearly this peak up here. But the minimum is down here on the edge. It's not a corner, but it's on the edge. So this is the worst. This is the worst, is what you have to do is you have to find this number 4 is the worst. And I just want to say that I understand the pain that I'm about to cause you. Is you're going to have to find what are called boundary critical points. Okay. Yuck. Just to let you know, it's not fun. Because here's the deal. You have to do a Calc 1 problem for each of these boundaries. There are 4 of them here. 1, 2, 3, 4 that you're going to have to deal with. I don't know that I want to deal with all those because it's going to provide me with, here, I'll even tell you how many. You can see on this boundary there are 1, 2, 3. You see those? There's a peak, a valley, and a peak. That's what we're talking about. 1, 2, 3. Over here, you're going to have 3 as well, a valley, a peak, and a valley. So that's going to give us another 12. I did not think through this very well. So let's just say that this is the one to set up so that it's easy to see. It's hard to, just because it's so much bookkeeping to do. So let's go on to this next one that's a little bit less bookkeeping. It's harder algebraically, just to warn you. So here's the deal, is this is this circular region. So you can see the circular region here. And so I have the function, that's this function here. And this is the circle that I'm dealing with. So let's go through those steps. This is going to be fewer points, though. By the way, here's the deal. Once you have all of those points, how many do I have here? 9 plus 4 makes 13 plus 12, 25. 25, I'll have 25 points. I compute the function value of every one of those. Pick the biggest and pick the smallest. Done. I know, it sounds so simple, but it's such a pain. So anyway, let's see if we can do this one. So step 1, sketch the region. So let me go ahead and sketch this region. You know what this looks like. It is a circle with a radius of square root of 2. So here's 1, here's 1 here. So there's the region. Region. Okay, that's number 1. Number 2. Oops, no, I don't want to use red. Use a different color. Okay, number 2. We're going to get the critical points in the region. I'm going to do this so that I can do it quickly. Oh, not f prime, it's f sub x. So 2xy, that's f sub x. F sub y is x squared plus y squared. Minus 1. Woo. Okay, double check my math. I'll give you just a minute, but I'm not going to be that long. Okay, you're happy with those? I'll set these equal to 0. Draw a line between them. So this one's the easy one, x equals 0 or y equals 0. So notice it doesn't say that x equals 0 and y equals 0. This is x equals 0 or y equals 0, and that's only for this side. We need to go over here. Okay, so move this over. So what I'm going to do is I'm going to take x equals 0, and if x equals 0, then I have 0 squared plus y squared minus 1 equals 0, which gives me y equals plus or minus 1. And when y equals 0 from the left, I get x squared plus 0 squared minus 1 equals 0, which is x is plus or minus 1. So this gives me 4 critical points. In particular, it's this point here, I'll draw them on the region, and then I will make a list. So you have x equals 0, y equals 1, x equals 0, y equals negative 1, y equals 0 with x equals 1, y equals 0 with x equals negative 1. So you have the 4, and you can actually see them on here. I believe this is the correct orientation. Y goes up, x goes over. You can see those 4 critical points on this little disk. Okay, next, we need to, no classification. Now we make our list. This is the first bit of our list, x, y. We're going to compute the function values at these points. So I have 0, 1, 0, negative 1, 1, 0, and negative 1, 0. Okay, now I need corner points. All right, so what are the corner points for this region? I know, there aren't any. So you have a couple of options here. See, this is tricky because one of the problems with a circular region is that you need to be able to evaluate what's going on the edge of this region, because we're going to get to the boundary. So the corner points, sometimes circles have corners, and here's why I say that. If when I go to compute my boundary critical points, if I separate this into a top half and a bottom half of the circle, then I have created a seam, if you will, or a place where I'll consider those to be corners. So corners don't necessarily have to be actual corners. It could just be a place where you're transitioning, like here, from dark to light, or light to dark, maybe around this circle. So there may be something like that causes. I think I can get away with considering the entire circle, because since x squared plus y squared equals 2, I can write this like this, 2 minus y squared, and just plug this in right there. So here I'm not using the square root. So if I did x equals the square root of 2 minus y squared, then I would be forcing myself to think about the positive and the negative. But here I think I can get away with this. So let's deal with this boundary. So let's, first of all, corners. So this is 3 corners. We're going to say that there's none for this one, but with the little asterisk. So now let's go on to the boundaries. There's just the one boundary. But you would do this for every boundary. Notice what I would do here. Up here, just let's back up for a sec. For this boundary right here, that is the boundary x equals 3/2. This here is the boundary y equals 3/2. I would take each of those boundaries, plug them into the original function, and then figure out where is the critical point on that boundary. It's a pain. This is yuck. This is where you're gonna really be sick of this subject. So I just want to name it for what it is. Okay, let's do the boundaries. There's just the one boundary. It's this x squared. So I'm going to plug x squared equals 2 minus y squared over there. And then, so I have 2 minus y squared times y plus y cubed over 3 minus y. There. I think I've done it correctly because I just replaced the x squared with 2 minus y squared. So that's the entire boundary, looks like that. Now I take this, and I'm going to call this boundary function number 1. So we're going to just call this f1. If there were more than one boundary, like here you have 4 boundaries, you would do boundary 1, boundary 2, boundary 3, boundary 4, and deal with all 4 of them. It's a pain. But fortunately, there's just the one. If you have a triangle, do I have triangles? I think I might. No, I don't have any good triangles here. I mean, this is almost a triangle. So if this was a triangle, you would just have boundary, the boundary along this side, the boundary along this side, and then the boundary along this. So there'd be 3 boundaries to deal with. Okay, so this is my function. Let me clean it up just a bit. So 2y minus y cubed plus y cubed over 3 minus y. This equals y minus 2y cubed over 3. I think I did my algebra correctly. Let me know if I got it. Yeah?
I'm just curious where the 2 minus y squared came from.
So the description of the boundary is that x squared plus y squared equals 2, which is this circle here. And so I took that, and I rewrote it like this because I happen to notice the x squared over here, that would be a candidate for making a substitution. So you take the boundary and you solve for one of the variables, but in this case I just solved for x squared because I could easily just pop a 2 minus y squared in there. All right, so far so good. Hopefully, I guess we're going to find out. Next, almost there. So this is what we're dealing with, and then this gives me, set this, derivative. Derivative f1 prime is 1 minus 2y squared. Oh, yeah, set that equal to 0. I get y squared is 1/2, which gives me y is plus or minus 1 over the square root of 2, or plus or minus radical 2 over 2, however you want to cut it. Once you've got that, we can go back to our original substitution. The original substitution was this, 2 minus y squared, wasn't it? And take each one of these. There are 2 of them. Plug them in individually. So you have radical 2 over 2. When y equals radical 2 over 2, I have x squared is equal to 2 minus really? Is that what I get? Does that seem right? Yeah, that looks right. Sorry, it just didn't look right. Okay, so this is going to be 3/2. So x squared equals 3/2. So x equals plus or minus radical 3 over radical 2. Yeah, write it however you want. If you prefer, you can write it like this. Radical 6 over 2. Okay, it's some decimal. You can use a decimal as well. And then when y equals negative radical 2 over 2, you get x squared is equal to 2 minus, radical 2 over 2 squared is 1/2. So that means that x is equal to plus or minus the same thing. So here are my 4 boundary critical points. Let me summarize. When y is equal to radical 2 over 2, I get positive radical 6 over 2 and negative radical 6 over 2. And then when y is negative radical 2 over 2, I have the same thing. Oh, we got 1 minute. We can do this. Negative 6, yeah. I'm getting messed up. Negative radical 2 over 2. Okay, so there it is. You have 8 candidates. So the last step, which is a little tedious, is to plug all 8 of those into the original function. That's this here. It probably would be helpful if you used Excel or some other spreadsheet maybe, but you don't have to. It's just a little tedious. I mean, I can do the ones that don't have the radicals. Those aren't bad. Let's see, just to give you an example, 0, 1, I get negative 2/3. And 0, negative 1, I get positive 2/3. So that's the height of this will be positive 2/3. And down in the little valley there, that's negative 2/3. I don't know how tall. Oh, I'll bet those are 0. Yeah, those are both 0. So these are both 0. So the only ones I can't do in my head are and you can see as you look around this, there are these waves, 1, 2, 3, 4. All of these 4 points, there's 6. How come there are 6? Okay, there must be something, I must be missing something. Interesting. I'll try to figure out what I'm missing.
Isn't the 2 minus y squared, when we plug it back into the original function, isn't that supposed to be squared because the x is squared?
Oh, it is supposed to be squared. Oh, yeah.
It's too late now, I guess.
Yeah, it's too late now. Oh, no, it's not supposed to be squared because I have x squared equals. Okay, I'm making a direct substitution. No, that's not my problem. I have another problem that I don't understand. I'll have to figure it out before, but you can see it's complicated, isn't it? Do your best with the homework. We'll deal with it on Friday. Stick around if you want to complain about your exams. If not, have a great day. I'm going to stop the recording.